Every time you unlock your smartphone, you are interacting with a miracle of engineering that shouldn't technically exist. Inside that device sits a processor with billions of transistors, each so small that thousands could fit inside a single human cell. But we've hit a wall. To make chips even faster and more efficient, we need to draw features so small that the very light we use to print them is too fat to do the job. This is the diffraction limit, and for years it was thought to be an unbreakable law of physics. To break through, engineers had to build the most complex piece of equipment in human history, the ASML High-NA EUV machine. It is a system so precise, it can draw lines on silicon that are only a few atoms wide. Standard EUV machines have been the workhorse of the industry, using a numerical aperture of 0.33. But to go smaller, ASML had to redesign the entire optical stack to reach a numerical aperture of 0.55. Think of it like a camera lens. A higher numerical aperture allows the machine to collect more light and focus it into a much sharper point. This increased resolution is what allows Intel and Samsung to print features at the 2-nanometer node and beyond. But increasing the aperture wasn't just about making the mirrors bigger. It required a complete rethink of how light travels through the machine, leading to the development of anamorphic optics. The EXE 5200B isn't just a machine, it's a logistics nightmare. It weighs over 150 tons, roughly the same as a Boeing 747, and requires 250 separate crates to ship. It takes 6 cargo planes just to move one unit from the Netherlands to a factory. Because of its extreme weight and the need for absolute stillness, standard factory floors won't work. These machines require specialized reinforced concrete slabs, often several meters thick, to prevent even the slightest vibration from the outside world. And then there's the price tag. A single high-NA machine costs approximately $380 million. That is more than the cost of 2 F-35 fighter jets, making it one of the most expensive commercial products on Earth. Inside the machine, the environment is a vacuum more empty than outer space. Any single molecule of air would absorb the extreme ultraviolet light, ruining the process. This vacuum must be maintained while the machine is operating at full speed. The light itself is created by a process that sounds like science fiction. A tiny droplet of tin, just 30 microns wide, is dropped into a chamber and struck by a high-power CO2 laser. But it doesn't just hit it once. The laser hits the droplet twice, once to flatten it into a pancake shape, and a second time to vaporize it into a plasma that reaches temperatures of 220,000 degrees Celsius, nearly 40 times hotter than the surface of the sun. This explosion happens 50,000 times every single second. Each one creates a burst of EUV light that must be captured and directed through a series of the world's flattest mirrors toward the silicon wafer. The engineering challenge here is mind-boggling. The machine must maintain the stability of these mirrors to within the width of a single atom, even as it is being buffeted by the force of 50,000 plasma explosions per second. It is a violent, chaotic environment on the inside, but on the outside, it is a masterpiece of calm, calculated precision. This is the only way to build the future of computing. To understand why high-NA is such a big deal, we have to look at the mirrors. In a normal world, mirrors reflect almost all the light that hits them. But EUV light is different. It is so energetic that it is absorbed by almost everything, including glass. To solve this, ASML uses Bragg reflectors, mirrors made of over 100 alternating layers of molybdenum and silicon. Each layer is only a few nanometers thick, designed to use constructive interference to bounce the light instead of letting it sink in. Even with this incredible technology, each mirror only reflects about 70% of the light. Since the light has to bounce off several mirrors before hitting the wafer, the machine needs a massive amount of power just to have enough light left at the end. The 0.55 numerical aperture system introduces a new problem, the angle of the light. If the light hits the mask at too steep an angle, it creates shadows that blur the tiny features we're trying to print. The solution is the anamorphic lens system. Instead of shrinking the image equally, it shrinks it by 4 times in one direction and 8 times in the other. This stretches the light to avoid the shadows, which is then corrected at the wafer level. This is like trying to project a movie onto a screen using a lens that is curved in 2 different ways at once, all while maintaining sub-nanometer accuracy. The math involved is staggering. To keep the mirrors perfectly aligned, the EXE 5200B uses a system of magnetic levitation. The mirrors don't actually touch the frame of the machine. They float on a cushion of magnetic fields, controlled by sensors that check their position billions of times per second. This allows the machine to compensate for the tiny vibrations caused by the plasma explosions, or even the footsteps of an engineer nearby. It is the world's most advanced active suspension system. If the mirror moved by even the width of a single atom during the exposure, the chip would be ruined. We are talking about controlling a massive piece of glass with the precision of a ghost. The silicon wafer itself is also moving. It sits on a wafer stage that zips back and forth with accelerations faster than a fighter jet taking off. It has to stop and start with nanometer precision thousands of times per hour. To track this movement, ASML uses laser interferometers. These lasers measure the position of the stage by counting the individual wavelengths of light. It's like measuring the distance to the moon with an accuracy of a few millimeters. The coordination between the moving light source, the floating mirrors, and the racing wafer stage is a symphony of engineering. Everything must be perfectly synchronized to within a fraction of a microsecond.